Okay, after lunch, after a beer, welcome to Chemistry 101. My name is Ken Coles. My chemistry buddy, Mike Gretzinger, we actually do have chemistry degrees, so there will be a test afterwards. Okay, so we're here to talk about something that is rarely talked about, and it's about the water that you use to spray. How many of you have ever thought about the quality of water that you use to spray? Couple? You've thought about it? Okay, second question is how many of you actually done anything about it? Yeah? Now that there's less hands that time. What did you guys do? You got a water test? You needed to acidify it? Okay, well we'll get into that. Basically, water is the universal solvent. So many different things will dissolve in water, and if it doesn't, we can do fun things like emulsify things. Anybody can you, what's the most common emulsified beverage that you know of? No. You put it in coffee though. Milk. Milk is an emulsification. So one thing you can do is you can shoot a little laser beam through a liquid. If you've got like a laser pointer. If that laser pointer disperses, it's usually an emulsification or it has suspended solids. Mike is going to talk about, there's basically 4 characteristics in water that we're going to talk about. Might as well ask you guys, so what do you think we're going to talk about when it comes to water quality? What was that? Soft water? Okay, you're going to write, Mike?
I got it on the other side, but not the same. So.
Okay, you can write soft, or how about hard water? Okay, we'll talk about water hardness, absolutely. If I had a prize, I'd give you one, Andre. I don't have anything. You can have a water on the trailer. What's another thing? That actually falls into the same category. Yeah, so no, you fail.
Solids. Dissolved solids.
Dissolved solids, I'll take that, yeah. It's a little weak, almost there.
Like I have neighbors that take water out of the irrigation pipeline.
Yes.
And there's a lot of dirt in there.
Okay, that's different. That's turbidity. So let's write down turbidity. Oh, you did? Holy shit. He was reading your brain cell. That's amazing. Okay, we need another one.
pH.
pH, absolutely. Now I can't remember what the last one is. What's the last one?
Salinity, alkalinity.
Temperature. Believe it or not, temperature is another one that we're going to talk about. So of those 4, which is probably the most impactful to herbicide efficacy? We had some hards. Number 2. So far, you're all wrong. Now, I know it is pH. So Tom says pH, you don't often have to worry about it, and that's true. A lot of the times, our spray mixes are between 6 and 8, kind of ideal. But when you're off, it will absolutely have the most significant impact on your efficacy. So pH is number 1. Now what's second? What's that? No. Soft or hard. That's the second most impactful. Followed by turbidity, yes. And then temperature. So temperature, you got to have some pretty big extremes. So we're talking like less than 3 degrees. So, or maybe you might get into that situation if you're really eager with the ultra early pre-seed burn downs or something like that. And then it's really after like 50 degrees where you get into problems. So we're not going to talk a lot about that. When you have some issues with your water quality, what are some of the things that you can do about it? That's a good thing. So I guess we'll have to teach you. So rates is kind of the chem company's best response to that. Up your rates. It will always help with whatever challenges you have. The other thing is adding the adjuvants. So adjuvants, they're usually formulated to either improve the emulsification, the dispersion, absorption, and the penetration into the leaf. So with that, I mentioned the companies. they try to register their products to work under the widest ranges of environmental conditions. So when we get into southern Alberta and we're dry and we're dusty and we have weeds that form these super thick, waxy layers, we don't always account for those differences. So even how individual weeds, they have different types of waxy layers. And the way we get our herbicides to penetrate is going to be different for every different weed. So there's actually a lot of room probably to do some fine tuning as we're getting into problems like herbicide tolerance that we talked about this morning. So those conditions matter. Everything that we've talked about, when you start adding them up, when you've got resistance, when you've got poor weather conditions, when you've got dust, or you've got turbidity, those types of things can compound to the point where your herbicides are almost completely ineffective. So we're talking about water content, volume, temperature, pH, the different types of herbicides that there are. You heard Tom talk about weak acids. Some of the weak acid herbicides are things like glyphosate and Liberty. Those are, like he mentioned, they'll bring the pH of your solution down to about 5 or so. Coverage retention time. So actually, if you increase temperature or even the basicity of it or alkalinity of it, it will actually change how the water surface tension rests on a plant leaf. So it can actually create a point that'll actually just run right off the leaf. So all of those little factors can add up and make a pretty significant difference. Time of day, droplet size, concentrations, humidity, and I mentioned dust already. So those are the main water quality attributes that we're going to talk about. We're going to try to be a little hands-on today so that you can actually learn what to do, like the two fellas in the back. They've gone and actually done some qualifiers on the water quality, and then we put some demos together here where we're actually a little surprised at the results that we've seen. So it's a bit of an eye-opener that I think there's a little bit of opportunity to do a better job on something that we do. I mean, when we think about it, it's almost like 95 to 99% of what we spray is the water. So I'll pass it off to Mike, and he's going to talk about turbidity and pH.
Well, Ken alluded to this, but you know, thinking about water, why is it that we don't, why is it we often don't think about water quality when we're thinking about our spray stuff? And I think the answer is really obvious. It's just because when it's working good, you don't think about it. It sits in the background. When you have good water quality, there's nothing to worry about because everything works, your herbicides work. It's only when you have something that's not working that you're like, oh, okay, every time I go and spray glyphosate, it doesn't seem like I'm getting a good kill, and I'm always filling up from my dugout. Or every time I mix in certain groups of herbicides, it seems like they're ineffective. Or every time I try and mix this one product that my rep is suggesting to me, it gums up in the sprayer, or whatever that is. So it's only when it doesn't fall in the background anymore that we notice it. It's kind of like breaking that fourth wall. So if there's any movie buffs here, I took a film studies course. It was a lot of fun, and what happens is you learn about all the aspects of film studies, and there's certain things that if all of a sudden you realize it's happening, it just ruins the whole movie for you and you can't watch it. So that's what I had on the back of this chart here. So, like Ken said, pH is hugely important. It's like the difference between watching a movie in color and black and white. So you watch a black and white movie, you know something's up right away. If your pH is way outside of that 5 to 8 kind of range, you're gonna know right away something's wrong with your water, and that's what's up there. When it comes to temperature, it's kind of like sound, right? If you got the volume down so low that you can't hear the show, you're like, okay, something's up. If you got it cranked so loud, you can't enjoy it. But in that medium range, and we're talking for temperature, like you said, like 5 all the way up to like plus 40 Celsius. So even if your water's from rainwater or you're storing it outside, water's got a really high specific heat capacity. That means it takes a lot of energy to change the temperature of water. And so that's one of the really cool properties that it has. The thing I'm going to talk about first or next here is turbidity and sediment. And so where that comes in, we took some samples. We got samples for these 2 plots here right from the canal down the road from us. One of the most common things we see with turbidity is that you'll have sediment going around. It's not dissolved, it's suspended in solution. things like glyphosate will bind to that directly, and then you lose your efficacy. And so what are some of the suggested ways that you can compensate for that? Did we talk about that already? Yeah, I think we might have. So you can increase your rate. That's one. What's another option? You get a better filter. So yeah, just filtering it out. There's also some things you can throw directly in there. I think I jumped ahead, but is aluminum chloride, is that the one I'm thinking for water treatment? What's it is called again? Aluminum sulfate. So you can add 10 to 60 milligrams aluminum sulfate in some conditions. The danger is that you're adding a positively charged ion into that solution. They use it a lot for water treatment and stuff, but you could potentially, if you add too high of rates, you could end up hardening your water, which is going to cause other effects that you're then going to have to counteract. So what we're going to do is we're going to look at real quick. We're going to get into our first little demo. So I need three volunteers for team 20 liters an acre water volume and 3 volunteers over here for 40 liters an acre water volume. So you pick what's your chosen spray volumes at. What do you like to spray at? 20, 40? 40, okay. So over here for 40, and a couple people over here for 20. It's a really quick example. This came from, I think, Kim Brown from Provincial Specialist. All we're gonna do, I got a couple little spoons here. We have 3 people. I need at least one per group though. And we're gonna mix in a little bit of soil until we can't see the bottom of our bucket anymore. And so that's gonna signify, you got some over there as well? Yeah, so give you a stick. Ashley will stir up one of your pails here for you. Sure. We're just gonna stir this pail up, and you're just gonna start adding a couple teaspoons, we'll call them, of soil until we think it's too cloudy that you can't do anything anymore. Okay, so Ashley's gonna stir that for you. We should probably replicate this a couple times to make sure that our results work out. We have a couple people doing this over here as well on 1 or 2 buckets. Any of these first 3 buckets here. Well, you got a little bee there.
So you're stirring.
We're just stirring. Stir until you can't see the bottom anymore here. This is our dugout water. So southern Alberta's got really high clay soils. We get a rain event. We get a lot of. Oh, I think you're almost done, Andre. I don't know. Can you see the bottom anymore? That's two stirs. How much have you guys done?
Only one so far.
One. Okay. We got two, and we're done.
We're done.
Yeah.
Okay, we'll dump one more in.
Dump one more in.
Okay.
You're pretty much done. You're pretty much done. How much we got over here?
We just did 2.
Two?
We can't see the
Oh,
bottom.
you keep going.
Keep going.
What?
Well, you must have done 2 big ones. This isn't working how we hoped. Let's try another one.
All right.
All right, sorry. Oh, that's a little baby one. Okay, yeah, keep going. There's our darker over there, I think. Tough. Try 3 or 4. Okay. All right, what's the consensus? 40 liters an acre. There's only 3 or 4? Maybe. Maybe. Did 1 or 2 make a difference here?
2.
2 max?
2 max.
You did go to 3. Well, we tried. So over here, what we're simulating is 20 liters an acre water volume. So it's gonna take us, or basically what's gonna happen, right, is we have, for the same amount of water volume, right, if we have a surface runoff, you guys should theoretically have twice as much sediment in there as we do over here. And so well, I think they were pretty large helpings, but I think 3 or 4 over there probably, and 1 or 2 over here. So that is about where we want to see it. So what that means is if I now go grab a jug of glyphosate and I start mixing this in, we've got twice as much sediment in that water to bound up that glyphosate. So that's one of the reasons we have to compensate with that higher rate. And what we did in these plots right in front of you here is we actually went, so this one here we did the 20 liters an acre water volume, and this is just like a third rate of glyphosate basically. And we've got 40 liters an acre water volume beside us over there. And you can see, I think we have a little better kill on this. This is from that sedimenty dugout water or canal water that we grabbed. And this is kind of one of the practices that we see from places where you can't necessarily pull clean water. Is there anything I missed on that, you think? Or anybody have any comments or questions? This is our 40 liters an acre water volume where you guys are. So there's more glyphosate being bound up to the sediment here, and it's being less effective than it is over here, basically. All good? That's basically what we got for turbidity, so I guess we'll jump on to pH. pH is fun as well. So on this table here, we have a giant pH chart. pH is power of hydrogen ions. You can remember power means it's logarithmic scale. So every time we go, I guess 7 is kind of our equilibrium point in the middle. Every time we go somewhere in another direction, it's a factor of 10 times different, right? It's not a linear scale. We're just gonna have some fun. It's distilled water. Where does this go? 7. This one I wasn't really sure. I just grabbed it from the shop. Anybody?
You spray with that?
I wouldn't spray with this. It could mix in or something. I think it's actually pretty close to 7.
It's not aqueous, so it probably doesn't have a pH. That's not the same solvent.
It's different. It's not in water. That's a very good point.
You could throw that shit up.
Oh, okay, trick question. Bleach. Where does this one go? How acidic? I got a cheat sheet. Oh, you should say acidic. You mean basic, right?
It's not acidic.
No, we're going basic. I just went basic. How basic are we going on bleach? What's that, 8? All the way, 10? I got 12.6 on my scale. Pretty basic. Baking soda. Worse than bleach, less. Let me double check, I put this. Sodium bicarbonate. Not very strong base. Good cleaner. All right, beer. Who likes beer? Yeah, 4 or 5, 4.5, somewhere like that. Lemon juice. Yeah, lemon juice, very acidic. All right, tonic water. A little surprise for later. 10. Our tonic water is about the same, about 2.5. We sent a water sample for that, so we got some cool stuff. Glyphosate. Ken kind of gave this one away. Yeah, glyphosate, weak acid. Soon as,
If it was in water, yeah.
if it was in water, it might even, so I suppose, maybe more. And we've got CH3, COOH, acetic acid. How acidic is acetic acid? Yeah, nice. You guys in chem class, yeah. We got a lot of it too.
Chemistry degree.
This is one more Tom
$30,000 worth just to say that one.
Tom Wolf talked about this one this morning on all the clean out stuff, ammonia. 7%, yeah. I go all the way up like 11.5. It's actually just less than bleach. Is that all I got in there? Okay. It's a good mix of stuff. So pH, massively important. But again, most of our waters are within that 6 to 8 range. It's really when we get outside of there, we start to run into trouble. So below 5, you'll have issues with the stability. You'll have some gelling. If you're mixing dicambas in, you'll actually volatilize, and they've done studies that measure how much volatilizes off, and you just never get it on the plant. And then if you're above on the other end, where'd John go? He asked about alkaline hydrolysis before. It's the organophosphates. So like malathion insecticide, your half-life in a tank it can be as little as a day for that half-life, or even hours depending on the pH of that solution. So if you're mixing it in, tank mixing with other things, you can basically make it ineffective. And if you leave it in solution more than a day or two, you're really going to lose efficacy on that sort of thing. So that 6 to 8 range is ideal. What are some of the ways that we can counter effect problems with pH that we might have? Most common way? pH adjuster. So what kind of adjuster do you use? You don't remember? Acidifiers. So citric acid is one that came up on all of the US forums. They just put straight citric acid in. But if it's just acidifying, it doesn't have, how do I spell that? It's missing kind of a key component that would be helpful. That's like a buffering agent. So if you get products like Li 700 or other things, what does a buffer do?
Must keep it from going too far.
Yeah, a buffer basically has this magical ability to basically maintain the pH. So it's got a weak acid and its conjugate base. And what that means is as other compounds are added in, it just kind of keeps circulating the reaction up to a specific point, but it can keep the reaction going and it keeps the pH at the exact same level, essentially. So they're really cool compounds for that. What are some of the other things we add in that affect our pH of our spray solutions? Any other additives anybody here uses?
Fix.
Fix? I don't know that one. Is that?
I'm just looking up what's in it. It's basically battery acid.
It's basically the same with the citric side, kind of a, yeah, sulfuric acid. AMS is one we're going to talk about on the hard water side, and kind of how it holds on to things like how it actually binds with glyphosate to make it easier to go into the plant and ties up some of the other molecules. And then I have on here, one thing nobody mentioned was the micros. So when it comes to pH, micronutrients can have a huge effect. And if you're tank mixing micronutrient products in with your herbicide, because that's your application timing, you really have to do a jar test and check that compatibility. When we did that biostimulant trial a couple years back, we had every single time we wanted to add something in, we had to check and make sure year to year, site to site and everything that it was compatible. And then we actually came up with one just the other day here. We're getting ready for the talks tomorrow on sweet corn and things like that. And there's a couple products that we like to use. Where are they here? We've got Accent and Armazon. Those are two common products for sweet corn or just even with regular corn, but they have contrasting pH requirements. And so if you have one product that you want to mix in with something and it needs kind of more acidic solution and you want to tank mix something with that requires a basic solution, you're just going to have compatibility issues. And so there's recommendations not to put them together, and that's why, is all because of the pH. I'm not sure there's much else I wanted to cover on there. Is there any questions on pH specifically? Or anything else we mentioned, or you want to get into kind of the nitty-gritty of all the hard water and stuff? Okay. Yeah. Utility. So it's like it does everything, kind of. I think there's a danger because everything's so specific. Like Ken said, there's certain groups, very specific groups of herbicides that require acidic solutions. Some require basic. It's really hard to come up with like a one-size-fits-all. And that's why looking on all the individual labels, some are very specific that they want you to add AMS to it or UAN or whatever it is. And some are very specific, like do not add this product. So it's hard. I don't know what else to say on that. Yeah, Yemi.
Yeah, so what is the optimum pH you can recommend for a good quality water?
Well, our distilled water is at 7, but I think anything inside that 5 to 8 range, you shouldn't be running into problems like the majority of the time. But outside of that, you really, once you start to go to the really two extreme ends, then you can have issues.
Yeah. 6 to 8 is pretty common, but like Mike said, and this is where it becomes complicated, right? You got to go to the product label. It'll give you the best recommendations. But now we're starting to tank mix like mad. So now you might have a conflict. You might have one that's better at a high pH and one that's better at a low pH. And then all of a sudden you throw in a micronutrient and you got a gel in your tank. So that's what Mike's talking about, is to do the jar tests. The jar tests, if you've never done them before, probably the best is just to get some little syringes. And then that way you can more accurately measure the product. You got to match the rate that you'd be mixing in your tank, and then look for precipitates, which is basically when things start to come out of solution and solidify. And that'll cause all kinds of issues with plugging. It'll wear out your nozzle tips and that side of thing. But if we wanted to summarize pH-wise, I mean, to John's question, the US has a lot more work and a lot more access to all kinds of different adjuvants. It's not the same here in Canada, so we're not faced with a lot of it. But I was going to save this for the end, but probably I think one of the biggest things when it comes to water quality is there's a lot more research needed on fine-tuning our adjuvants to local conditions and to specific weeds in particular. We've got a Roundup Ready or glyphosate-tolerant kochia issue. We should be looking at different ways of getting better translocation and better retention. So I'd suggest that that's an area that we really need to work on. If we think back to pH, and this has already been reinforced by Tom, what are the types of herbicides that we do not want to have our pH below 7? Group 2, especially the SUs, the sulfonylureas. When I was working for Monsanto, they came up with a product called Anthem. Next thing you know, it went to market and everybody was having these disgusting gelling mix. And it was a big, big panic, and all they had to do was add a little bit of this, a little bit of finish, and it solved all of the problems. That was like millions of dollars of issues for a little bit of a basic product just to adjust it. So keep that in mind, and also to keep that in mind when it comes to sprayer clean out too. So it's a good opportunity to reinforce that. Okay, we're gonna move down to the next part of the session, just a little ways down here. So I got a trick question for you guys. What does alkali mean? We always hear like, oh, farmers, oh, it's alkali. What does that mean? Sorry? Somebody said it right. That's where everybody's heads goes, but it's wrong, right? Alkali actually means basic. What we talked about on the pH side, anything above a pH of 7. The reason it's basic is when you want to get back to the periodic table, do you guys have this all memorized still? I actually knew it all at one point. I do not anymore. On the far left, we have the alkali metals. That's why it's called alkali. It's a type of base. It's not all of the bases that are out there. Right beside it, so in the alkali metals, we've got sodium, potassium. When they dissociate in water, they have a +1 charge. When we're talking about acids and bases, there's different ways of describing it. Sometimes it's hydrogen ions being pulled away from water. Hydroxide is the base. There's other, it's whatever can donate an electron is also a base. Right beside it is the alkali earth elements. So that's where the magnesium and the calcium come in. They dissociate as cations with a 2+ charge. So whenever you have more charge, it's more attractive to a negative charge. So now that you know that, alkali is not saline. What is saline? Yes, it's dissolved salts. Dissolved salts is almost no different than what you were talking about, Will, total dissolved solids. Pretty much the same thing. So we can measure for that. The easiest way is a little test called conductivity. So that's EC. Same thing that you would do for salinity testing. Anything that's dissolved in water will conduct electricity. The more elements or the more dissociated molecules in water, the higher the current. So then you can basically guess how much does your water have for conductivity. So that's the first test. When we talk about hard water, somebody said soft water. What is soft water? That's actually not a bad answer. Basically, no dissolved solder. What's the best example that we can get of soft water? Sorry? Rain. Awesome. So rain is basically the softest water you can get, except that sometimes it'll pick up a little CO2. Mike talked about pH and everything. Anything that has CO2 dissolved in it becomes an acid. So that's why the beer and the Schweppes are down on the low side of things. So whenever you mix CO2 from the atmosphere and water, you create an acid. So knowing that now, what is hard water? Hard water is basic. Yeah. What's in hard water? Sodium is correct. You can put sodium up there. Sorry? Calcium is correct. Iron is correct. Could be the 2+ and the 3+, yes. Anything else? Thank you. 2+. All alkali earths and alkali metals. Are we missing something? Chlorine is no. That's a negatively charged element. That's not, it would contribute to overall hardness, but it's not a main contributor. Did we get them all? Aluminum could be in there.
Where's that periodic table? Who still has their periodic table memorized?
Thanks, Wind. So those of you that know hard water, what are some of the problems you have in your everyday life with hard water? Yeah, that's if you have iron in it for sure. Scaling. Scaling is one of the biggest issues. So hot water heaters, kettles, all of that junk that you've got left over in there, that's all because of hard water. When we talk about sort of the scales of hard water, they say soft is 0 to 60 milligrams per liter. When we talk about hard water, I'm sorry, I had to step back a little bit. The two most important elements are the calcium, you can circle that, and the magnesium. Those are the two single biggest. It's basically everything else is almost insignificant. The reason we have hard water here is because of our limestone mountains. Limestone is calcium carbonate. Can you write that down, Mike? Carbonate is the sort of unifier. It's a base. We convert every molecule in the water to a calcium carbonate equivalent. So whenever you're looking at water hardness, that's the unit of measurement in milligrams per liter. You can adjust, you can have a different base, but it'll have a different molecular weight, and then there's a conversion to get it to calcium carbonate equivalents. So 0 to 60 is soft water. You want to put that down? Moderately hard is 61 to 120. Hard water is 121 to 180. And then very hard is anything over 181. What is your guess that our local tap water is here? That's pretty much bang on. Who said that? Nathan's kid said that? That's pretty impressive. Yeah. Yeah, our tested was 170. So if I had a prize, I'd give one to your son. Yeah. So the scaling, you guys, there's the other issue that we have with hard water. What does it do to the soap? Right, it doesn't really lather. So when you have a bar of soap in a hard water, you've probably all done this at your grandma's sink back when they used to make you wash in the sink. As soon as you put soap in there, the water goes white. And it doesn't really froth up or doesn't really foam. If you did that with the rainwater, you'd have lots of luxurious bubbles. So the hard water actually reacts with the soap, and then it binds to it and it creates soap scum. And that's why it's harder to clean off, it's harder to rinse off. And then when you go somewhere else with soft water, you'll sit there and wash your hands and it doesn't feel like it comes off. And that's because we're so used to the hard water and the feel. So when we talk about soaps, it basically, you need twice as much soap to do the job. What happens, do you think, when we're talking about spray mixes in hard water? What's similar to soap in spray mixes? Yeah, all of our adjuvants are soap. It's basically the same thing. So as soon as you start having hard water, it interacts with the herbicide mix, and it basically means that you have to do just like you do, is use more laundry soap and more dish soap. You got to add more herbicides. So that's a bit of a problem because herbicides cost a lot of money, right? So we promised you to play around and figure out a few things, how you can test your water. We did put some plots, we'll look at them in a minute, but there is one thing we can add to a spray mixture that will deal with, help offset the problems associated with hard water. And that's ammonium sulfate. The ammonium sulfate, that's just fertilizer. Like, you put it in a small amount, it has a twofold effect. Usually we'll do that in a 1 to 2% mixture. If you have hard water, what the ammonium sulfate does is create sulfate ions. Sulfate ions is SO4 2-, and it just likes to bind with the magnesiums and the calciums. So it takes that hardness right out of the water. So that's the first benefit from it. The second benefit is that the ammonium ions actually helps improve uptake at the leaf side of things. So it's got a twofold improvement, and I'll show you our plots in a second. It's actually pretty amazing how well it works. Glyphosate is a weak acid. Weak acid herbicides struggle with hard water. So it's the most studied herbicide of all when it comes to hard water. At the label low rate of glyphosate, for us, I told you what the hard water definition was 180, I think. We don't have to worry about it until we hit 350 milligrams per liter or parts per million. So you can write that, Mike. This is an important take home. Once we hit 350, watch out with your glyphosate at the low rate. Once we hit 700, watch out at the high rate. So that's when we need to consider putting that ammonium sulfate to help offset and counter effect the hard water. Yes, sir?
Is that really bottle of water that comes with some of the packs?
Sometimes, yeah. It could either be ammonium sulfate or UAN. And what I haven't talked about yet, it's part of hard water, is bicarbonates. And then we've got a plot back there we'll take a quick look at. So remember, hard water is going to hurt the weak acids, so glyphosate, Liberty, those types of things. Bicarbonates actually will interfere with group 1 herbicides, especially the DIMs. So like your selects and posts and all that sort of thing. So if you've done a test, so first thing you would do is like an EC test, and if it's over 1,000, you better look into what's going on. The EC test, what we're going to do right now actually is give you guys a chance to try these out. This is a 16-in-1 water kit. This is the first, simplest, easiest way to start testing your own water. Super cheap. The other one is to get a little handheld, and it's a little more convenient and a little more accurate. We just picked one of these up. So this will do electroconductivity, total dissolved solids, pH, temperature, something else that I can't remember. Probably not that important. Okay, so anybody that wants to try a paper can come on up right now. Grab a cup. As many as you'd like to try, come on. Give it a go. Okay, if we just get one or a few cups of water, everybody can just go dip in. So just start filling up enough to dip one of these in.
Which one?
This one here. Either of those. Yeah. So this is the water from my house. This is my sump pump water. Okay. We got enough? Anybody else want some juice? Looks a little yellow, yeah. It's basically shallow well groundwater.
Is it high in rust?
No, there's no iron in it at all. No. Okay, so dip. Where's Mike? He needs some help. Okay, we can hand these out. Dip for 2 seconds, wipe off the excess water. Just pass those around, please.
Here, I'll pass them. Oh, yeah. Oh, thanks.
And then here's some paper towel just to dab it off after a 2-second soak. You can bend it, curve it.
Who would like one?
Dip it and dry it. It's like instantaneous. It's almost too quick.
Anybody else? We got lots here. Yeah, dip the whole thing in for 2 seconds, pull it out and dab it off with some paper towel. Anybody else here? We got lots. It's playtime. Lots of colors.
What's the difference with esters and amines?
Amine, like a 2,4-D amine, will be affected by carbonates, whereas the ester will not.
Yeah, I just know when you do a spray water test, it comes back with recommendations.
Where'd my box go? No, down here.
What's that?
Did we use all the groundwater?
Oh, here's some more right here. You can actually use this.
Yeah, that's a different one. What did you get? Ooh, extra hard. Cool. Is anybody else looking for one to try? Absolutely.
It's like my hot tub strips.
Can I grab this for a sec? I think we got a paper in here too. Okay, basically, you're gonna slide it and match it up. Try to write down and take note of a couple of those things like hardness, and we'll be able to tell you what it actually is. 2 seconds. 2 seconds, wipe off the excess. And then there's a chart here that you got to compare. The whole thing needs to be in for 2 seconds. And then wipe it off. I think we're going over on time. Yeah. I don't think it's something that you need to put in everything. You know, if you don't have hard water, although I think it might be worth studying that further. Yeah.
In crop spray, anything in crop. Yeah. I know they've you know, when back in the old Achieve days, they'd say to use it if you thought you were having trouble.
Yeah, but they didn't know what they were doing it for.
No.
Yeah. 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 Ammonium sulfate. It might acidify it a bit. Yeah. I don't know.
So if you're using it won't blow away.
Any of those,
Okay, so we're running a little short on time. Those of you that did it, I'll tell you what the actual results were. For the groundwater, we had an alkalinity of 525. Bicarbonates were 641 parts per million. Total hardness was 1,620. So that's getting up there. That's just water from about 10 feet down at my farm. So once it's gone through the ground, that's where it picks up all of the different minerals and hardness. So let's take a quick look at some plots that are almost the same hardness. Now, I'll get you guys to turn around and look this way. Okay, so this is hard water. The low rate of glyphosate, it's actually a 2/3 rate. We wanted to make it a little bit obvious. And we actually didn't get much control. That hard water really did impact that control. It should have killed these little grasses. This stuff's even harder. This is about the same hardness of that water that we just tested. Basically no control. I would expect to see something. Check out the AMS added. Now you can actually see some dead weeds. So it's really quite dramatic when you think about it. So if you've ever gotten yourself and you don't know the hardness of your water, check it out. It's worth checking out. It makes me want to do a little more research into if we can just improve overall efficacy with the AMS. So then we got even crazy hard and basically no control at all. The very first plot that Mike didn't measure, he actually sprayed it with his Schweppes water, which had a pH of about 3. Go look at the control over there.
All
This was a bit of a shock. It's probably the best plot. So really what tonic water is just bubbly water, so it's acidified. And it will work better in an acid condition, but if you get it too low, you can actually run into solubility issues with glyphosate. But again, I start thinking about opportunities. Maybe we should be looking at this on a pre-seed burn down. Yeah. Yeah. This one here was tonic water. Yeah.
Like pure tonic water or just like
Tonic water and glyphosate. Yeah. Yeah.
but like not added to water, like just pure tonic water.
Yeah, which is, it's water.
Yeah.
It's just bubbly water. Yeah.
But with a pH of 3.
Yeah, it's carbonated water. Yeah. I wouldn't fill up a spray tank with that, but there are ways to get it to that acidity a lot easier, a lot cheaper. Okay. So then the take home here is just understand your water. There's some simple things you can do to test it. Of course, you can take a sample and send it to a lab and then get the full write-up on everything. It's not that hard to understand. If you need help, we'd be happy to help you. I mentioned the bicarbonates. The UAN is the solution for bicarbonates. So that, again, is just another liquid fertilizer that will help with hard water in the group 1 things. And I think that's important because we've got a whole bunch of group 1 resistance for wild oats. So anything that we can do better on getting those under control is worthwhile. So thank you very much. I think we have to get going. Are there any last minute questions?
So that control is just regular water, not hard?
That one that worked over there had AMS in it, ammonium sulfate, so it's just a fertilizer at 1 to 2%. Yeah.
So is there an order to add this?
Yeah.
Mixing
it
order?
can make a big
Yep.
difference, yeah.
So add it first?
Oh, the AMS part? Yeah, usually you use any of the adjuvants or additives is usually the last thing you put in. Yeah.
It's usually, but
Yeah.
I think in some of the
Unless you need a pH adjuster to get solubility.
conditioners,
Yeah.
then you probably want to add them first,
Yeah,
so that your
'cause I
water
think
is where you
that's
want
what
it to be.
said was to add it first. And
Yeah,
then
which is
That could be.
different than the conventional wisdom of the going through your normal mixing order, solubles.
Because it's not an adjuvant, it's actually a pH adjuster.
LI 700 is always the question, first or last.
Yeah.
I had a
Because-
label printed,
because
I
it's-
don't know what it
because it's
says, I
both.
don't remember.
Well, it's a buffer as well. So
Yeah,
it's
it has a lot of different.
LI 700 is a pH, it's an acidifier, but it's buffered at about 4.5. So
If you want to drop it low, you put like
I would probably dissolve it first in a more basic solution and then bring it down. So I personally, I think last would be my suggestion.
yeah, but if you put it in last, then the pH wouldn't happen. Because
It would still bring it down. Yeah. Like everything, almost everything dissolves better in basic. A weak acid, all those dissolve better in basic. I'm getting told we have to wrap up though, so thank you so much, everybody.
thank you.